So one of the earliest look of flows that was done was an experiment by Reynolds himself, right? He's the one that came up with this whole number, and it was a way to quantify how this experiment changed based on this one number. So he had some large reservoir of fluid, and then it fed into a very long tube, and then he put a little injector of dye right in there. So then coming out of this, you have some volumetric flow rate, which is A times V, the cross-sectional area of the pipe, and then a velocity of it going down the pipe. And this is where you get this classic look of something happening where for internal flows, if this was the case, if this Reynolds number was quite less than 2,000, when this dye was released, it stayed where it was and just moved down the pipe. It didn't really change much. And again, this number of 2,000 is restricted to this internal flow that we're talking about for this first section of class. This is not the case for external flows. There will be a different Reynolds number for turbulent and laminar for external flows. But right, this first experiment did this. We injected some dye into this fluid that's moving down. It's moving down because there's a lot of liquid in a tank that's pushing it out of there. I think you did an experiment for that in Fluids 1. And this is one of the first looks that happened. Well, if this number that I can calculate, right, that's the rho dV, and then I had the viscosity, less than 2,000, I get something that looks like this. And then very kind of roughly, if it was around 2,000, which is kind of very rough, then what happened is the dye would kind of like oscillate, right, start to move around, oscillate down, right down the pipe. It didn't get too crazy, but like you just notice that this dye stream was kind of wobbly around. So this is, transitional is what people were to call it. And then of course you had once that number got, in undergraduate we say strictly greater than, but really had to be a lot bigger than this. If it was a lot bigger, then what would happen is the dye would come out and then it would immediately just start mixing down the pipe. So, right, this is the right characterization of turbulent flow. It's just that turbulent flows have a great mixing behavior, and it's quantified by this Reynolds number greater than 2,000. So those are just wonderful, right, views of how these non-dimensional numbers can tell you about the look of this flow happening, right? We could just write it again, right? So this less than 2,000 is what we call laminar flow. If it's greater than, we call it turbulent flow. And then kind of roughly what we say, right? If it's around there, it's in this transitional flow regime. And these usually you kind of want it a lot less than 2,000, a lot bigger than 2,000, and kind of around 2,000. So, but for all classes and calculations, usually these strict inequalities will suffice. So sometimes, I think sometimes you can even say equal, but I wouldn't recommend doing that.